Hello, in this presentation, I would be designing a rule-based system or a logic-based system for the general problem of motion planning for multiple autonomous vehicles. The introduction to the problem is a separate video. The link should be available in the video description. Now, here I am doing something that humans have been doing since long. When we teach a kid how to drive, we tell him or her if there's an obstacle ahead, all you need to do is to steer right and overcome the obstacle. So we tune in such kind of rules, what to do in what kind of traffic into the children or into other students whom we are teaching driving, and after we've taught them these rules, they are ready to drive. They get their traffic driving license and they simply drive. So these rules, which are sometimes traffic rules, sometimes best driving practices, if I can teach my autonomous vehicles all these rules, my task would be done. I'll teach this vehicle just as a child to whom I need to teach driving. I'll teach the same driving rules that we teach children and the task is done. Of course, humans understand the term behavior and what to do in a very broader sense. My machines do not do that. I'll need to be aware of this. And that's all that I'll be doing for this presentation. The major concept over here is that in any planning scenario, there are deliberative systems which construct nice trajectories like this and tune them, and they are reactive system which basically see there is an obstacle ahead, there is something at the side, so this is the best way to move. So they are deliberative system and they are reactive system. Here what I would be doing is that I would be saying that this is a part of the entire road. So maybe there are many obstacles like this, there are few vehicles like this. You see an obstacle in front and you make in this obstacle avoidance trajectory, which by the way will be a behavior in our system. So if you see this part, I made a trajectory, hence I'm being deliberative in this region of the map. But if you see my overall map, it's a very long map, there are so many things happening. I just saw something in front and I made a reactive response where in place of a single move, it is now a slightly longer reactive response to it. So if you see this part of the map, I am deliberative, but if you see from a very broader sense, I am reactive. And that's why I'll be saying that it's a balance between deliberation and reactiveness, where there is some deliberation used to check the precondition of the behaviors, to check what trajectory the behaviors cause, and there's reactiveness in a very broader sense. So very quickly, whenever I need to overtake a vehicle here, these are in fact some very general assumptions that we have been making. If I'm overtaking this vehicle out here, I'll commit to because it's a kind of reactive system from a broader sense, I'll commit to the overtake. I'll say the overtaking is happening without considering scenarios like this into the future where the road might narrow down. So I'll assume my road is straight, continues to be straight. In this very case, the overtake would not be possible if the vehicle dips to one side, and it might take very long or it might take very short to do so, only after which I can overtake. So I'll assume my road to be long enough so that there's enough time for this to dip and my overtake to be completed. I'll not assume that there are these kinds of roads where there's an intersection here or there's a crossing here or there's something because of which the road ends. So my road is infinitely long. And of course, in the same scenario, if I'm attempting this overtaking and this vehicle seems to be moving straight, I'll assume that in future it will not, or immediately it will not do the same thing due to any obstacle or this thing. So it will itself not dip. I'll assume all the vehicles to be driving straight ahead. So all the vehicles are projected to be driving straight ahead with some positional and velocity uncertainties, of course. Now straight roads come in a variety of formats. One are single ways where all the vehicles travel in the same direction. The converse is also called as a single way. where they travel in the opposite direction. The other roads are dual carriageways with a physical boundary here, so there's an obstacle that people add so that the vehicles here travel straight and the vehicles here travel straight. And of course these two concepts are similar because this maps to this and this maps to this, so I can always convert these roads into these roads. The other are in more general that we are more interested in. There's no physical barrier here, there may be a road. In general, these vehicles have to travel like this and these vehicles have to travel like this. But obviously what might happen is a vehicle here may sometimes occupy this position out here. It may travel in wrong side or part of the wrong side. Now we analyze that this is barely legal. Very few times this happens, and we analyze why does this happen. It's only because of one reason. There's only one reason why things like this may happen, is that if there was a very slow moving vehicle, say a bicycle or a very slow moving car ahead, and this is a very nice car out here, so it might want to overtake, and it can only overtake if it occupies partly the wrong lane, which is what we call it as a single lane overtake, because overtaking took place at the single lane. So in this entire presentation from now on, I'll be assuming that the roads are single lanes. I'll be assuming this kind of scenario where the marked lane here becomes a solid boundary out here for all the behaviors, for everything that we do in traffic, except for when I study this behavior of single lane overtake, in which I'll assume that the road is a dual carriageway and there's a virtual boundary out over here. Now something interesting that happens out in the roads, suppose I've got a long road here and there's a nice little small obstacle out here and I'm driving out here. Some people may maintain only this much of a distance from the obstacle, which is fair enough. Some may maintain this much distance, which is again fair enough. Some may take more distance, which is very bad. I mean, this is just kissing the obstacle, so there is some risk involved here. This seems fair enough. There is a little amount of risk, but the obstacle is far away. We are not that bad at drivers that we need more risk. The vehicle will not skid or it will not slip more than this amount. And this is being overly cautious, but then in general we know that they are all these kinds of drivers which is a continuous scale. So the maximum separation that you maintain from the obstacle or the other vehicles is a driver property which more or less leads to aggression. This is a more aggressive driver. This is not an aggressive driver, but still to some extent it's aggressive, and this is a very less aggressive driver. So the maximum separation is always under a driver property known as driver aggression. And we take another scenario where there's a vehicle out over here. I'm following this vehicle. I need to overtake. Now some drivers would say that this the projection of this vehicle, that this is enough distance, I can overtake. Some others would say that no, this is a very risky overtake, this separation is too less, I may slip, I may not be able to control my steering well on time, something may happen, this vehicle may move a little bit. Others will say that this is a risky driving, so I should not overtake. So the drivers who say this is a valid overtake, I have enough of separation even though low, are more aggressive drivers. They take the minimum separation needed for overtake or the minimum separation needed for any behavior. It may be an obstacle avoidance behavior. So they take the minimum separation for any kind of behavior to be exhibited as less, and even with less separations they initiate the behavior, and some others are more cautious. So the minimum separation that the driver maintains and the maximum separation that the driver plans to maintain, they would be called as the aggression factor out here. And that is what is the general design methodology of any general discrete rule based system. Basically not much do you see these days that people design a discrete rule-based system for any problem, which is what we have done. So I'll speak in a little about what is the general methodology of such kind of system. Basically, we look at all the kind of scenario that the vehicle may be seeing into the future. There may be an obstacle, there may be some vehicles out here, or there may be a vehicle directly ahead out here, a vehicle out here, a vehicle out here, and a vehicle out here. And this is what we need to plan. There may be other scenarios where there is a vehicle out here, there's a vehicle out here, there's an obstacle out here. So we see all the various things out here, all the various database of scenarios that a vehicle might interpret. We decide what we need to do. Like in this, it may be overtaking an obstacle. In this, it may be trying to overtake from here or from here. Here, it may try to overtake this vehicle out from here, or it may actually follow, seeing that something bad might happen into the future. In fact, it's a risky this thing, so it will actually follow this vehicle out here. So we see in this database, we see why vehicle is doing something, and we simply map them into a number of rules. The rules simply say if whatever is the type of scenario, then whatever is the type of actions to be taken. And of course, we need to be very careful when we frame in such kind of scenarios, or we frame in such kind of preconditions. We cannot frame in a rule saying that if you are, this is a vehicle being planned, there is a vehicle directly ahead at an angle of 0 degree, and there is another vehicle ahead at an angle of 45 degree, then initiate the overtake. The problem with this is, of course, what will happen is that if I move this vehicle a little here, the scenario hasn't changed much. The human thinking will obviously say that it's almost the same thing, but it will be a different rule. So if we cannot be too specific in our rules, if we are too specific in our rules, we end up in too many rules to frame, and the human expert framing the rules expires. He's unable to make the entire rule base. And we cannot be that general in our rules that the rules no longer hold. So suppose in the same scenario we say that if there's any vehicle ahead, simply overtake it. I assume that this was a kind of scenario, and I said simply overtake it. It means simply overtake it. And I said this rule will always hold because I'm not being trying to be too specific. What happens? This is again a vehicle ahead. Now it overtakes like this, whereas in general this was always a better overtake possible. So I need to make sure my rules are not general enough, they are not specific enough. Luckily for our system, the rules would be overlapping in nature, means many rules can have the preconditions true. And it's not a fuzzy system, so it's a discrete system. So we will be selecting only the rule with the highest priority. So the rules are prioritized in nature. A higher priority rule happens to be better than a low priority rule. So if two rules have the precondition, the highest priority rule will be selected. And of course, it's a discrete system, so I cannot overtake while I cannot avoid an obstacle while I'm also overtaking. There's only one thing that I'll need to do. And similarly for the other behaviors, I cannot model and I cannot perform dual behaviors simultaneously. And in general, it's an iterative process. What I do is that I frame in some rules using this database. I simulate the system. I see what happens. I normally see that vehicles are acting very weird because my rules are wrong. So I change my rules. I may make some of them more general, I make some of them more specific, I add some more rules. I see what's the anomaly and I add rules, and I keep on doing this. I again simulate, see what's going on until I get the best system which passes everything that I can think of. So that's what my general methodology would be. From now on, what I would be doing is that I would be seeing different, I would be taking different, I would be giving you different scenarios like this, and I'll simply say what the precondition would be, and in that precondition what the action would be. So from now on, the presentation would only be based on giving you scenarios like this, and together we'll decide what should be the actual action to take place, and we'll simply generalize that in the form of general precondition and general actions. And just to be clear how the vehicle performs, or in the previous slide I said simulate the system. Suppose there's an obstacle like this. I said, oh, my best action is overcome the obstacle. I will be overcoming the obstacle using a behavior like this or a trajectory like this until I come here, and then again I'll see what's the situation. Suppose there's a vehicle out here, I'll be saying overcome the vehicle or overtake the vehicle. So I'll be constructing this trajectory when the vehicle comes here, I'll again be asking this question. So it's an iterative process I keep on seeing. Now, the problem out here is that I cannot blindly follow this trajectory, or I cannot blindly follow this trajectory. There might be many there might be many things I had been blind to while formulating this trajectory. There might be a vehicle out over here. I did not consider it while framing this trajectory, or there might be other things. So that is something new in this rule-based system, that while I am following a behavior, while I am taking an action, while I am following a trajectory which represents a behavior, there are some in-behavior specifications which will guide me what to do, and this in-behavior specification can tell me cancel this trajectory, take a new behavior. They can tell me that do follow this trajectory, but arrange your speed in such a manner. It can modify this trajectory, or it can do anything like this. It can cancel a behavior. I can cancel a behavior. I can opt for a new behavior, or I can modify my speed in reaction to this behavior. So that is what are my in behavior specifications. The rest is what happened in the previous slide. I'll keep on iteratively following this process. And these are, now a vehicle behavior is a very rich thing where multiple things happen, but then when we generalize enough, these are the 12 behaviors or the 12 rules that I have got, and the following slides would be presenting each one of this. I'll be speaking a lot about this behavior, which is a normal overtake behavior. Overtakes are very critical to generalize. They are very critical to find out when to do, when not to do, and how to do. And I'll be speaking a lot about the single lane overtake behavior right here. So these are my two major things that I would be presenting in the subsequent things. The rest are very simple to see what will happen, and that's of course my first behavior where I see an obstacle out here. There might be a complete obstacle grid like this. Like I've shown only two of the obstacles. There might be a grid like this. So in such a case, what do is that we take a sweeping line and we make it travel across the entire road. Now, when I'm analyzing a particular sweeping line, suppose I'm analyzing this sweeping line, I'll only be seeing this sweeping line. I'll not see anything ahead and anything behind, and I simply say if this is my sweeping line where there was some feasible region, there was an obstacle region, it cannot be entered, and there was another feasible region, I finally need to maximize my lateral separations. My objective is to keep as large separation as possible under the threshold given by the driver aggression. So this is better than this unless this segment was really wide enough. And here I select the best point. So my vehicle is initially at this lateral position. If I find out the midpoint of this, which is a point which maximizes the separation, I see that the vehicle will have to steer by a large amount in getting to this point. It's too much amount of lateral distance. While I do not need that high lateral separation, the driver aggression is not that large. So I select this point, which is, and this is what is the maximum driver aggression or the maximum separation, which I presented at the aggression factor out over here. So that's the point that I selected for this region. It will be nicely for these, it will be just these points. There is no obstacle out here. For here, it is basically the midpoint. Here we see that the maximum separation needed as per the driver aggression values is not being met. So the best that I can do is to maximize the lateral separation. So I select the midpoints in all these areas. So I'm considering where my sweeping line crosses the obstacle. I've got 4 points A, B, C and D. I need to select one of them for subsequent behavior. Suppose I select A, what happens? The vehicle travels from L to A, it sees an obstacle like this ahead, so it needs to further dip in towards this point B. So there's one steering event required here, one steering event required here until it reaches B. and from there on it can travel straight. If I select B, it straight away goes to B and then it can travel straight. So traveling straight from B is not a problem. If it goes through C, now when I formulate a trajectory which connects L to C, it'll in fact be a trajectory which might get into collision because of this obstacle out here. A trajectory to C would go something like this. So my vehicle is colliding out here. And similarly, if I construct a trajectory to D, it will not be possible. It's colliding out here. So out of A, B, C and D, A and B are feasible, out of which B is good because it enables me overcome the entire obstacle framework by a single steering event, and hence B would be selected out over here. Now that's some specific example. In general, I would be generalizing this concept and I will say that always the leftmost or the rightmost point is selected. Like in this, B was the rightmost point. There was no point lying more right than B. I didn't have a point out over here. I didn't have a point out here. So the leftmost or the rightmost point will always be selected provided we can construct a trajectory till that point. That will be my obstacle avoidance point. Now I particularly need to check in the feasibility because of a general or an obvious thing. Suppose there was an obstacle like this. In this case, it will not be feasible. So suppose there was a more rightmost point out here. This is even more right than P, and I select this. Unfortunately, this is an obstacle out here. So now I cannot, selecting this will not help because I cannot construct a feasible trajectory till here. So my point needs to be rightmost, number one, and it needs to be feasible, number two, in order for my point to be called as the obstacle avoidance point. And once I get this point, I can simply construct a trajectory from my current point to this point and make the vehicle travel this trajectory. And of course, I know that when I reach this point, my process is iterative. I'll again call on for the same behavior. I'll again search for the best behavior out of my entire pool. So it's obstacle avoidance strategy says select the rightmost and the feasible point and use it for navigation by any trajectory like this, and that this is what I simulated for a bigger grid. Of course, the obstacle avoidance point would happen in multiple iterations. First, it will travel from here to here. It will see this obstacle. It will travel till here. Then again, it will use all the available behavior set pool. It'll select obstacle avoidance behavior. It will travel till here, and in the fourth pass, it will travel till here. So it happens at multiple passes. Now, this is when the vehicle has maximum separation available as per the driver threshold, so it need not care for anything. Here we see that the vehicle used this trajectory. It did not use a trajectory like this which had even larger separation. That's because this separation was larger than what's maximum as per the driver threshold. Here we see that the maximum separation as per the maximum driver threshold was not available, and hence it clearly chose the midpoint. And here again, it used this trajectory. It did not use this trajectory which had even larger separation. It's because of the maximum driver threshold. So in future, I'll not be saying that when does the vehicle use the midpoint, and I'll not be saying in the future slides when does the maximum driver threshold or the maximum distance that the driver intends to keep or the driver aggression. I'll not be saying in the future which one of these two factors is active. I'll just say that I can get the best possible lateral positions out for any behavior. And the second behavior is centering, and centering is again a very simple behavior. Suppose I'm driving all alone at this road like this. It's a single way, of course. I'm driving alone in this road like this. There might be faster vehicles ahead, but then obviously if I'm slow and this is fast, I'll never collide, and there may be still slower vehicles behind, but of course if I'm slow, this is very slow, I'll obviously not collide. So what I can do is that I can slowly and slowly drift towards the center of the road, and that's what I'll do. I'll select the last point out here in the road segment in which I'm being in which planning is being ahead, which is at a large distance from here, and I'll simply travel to the center of the road. This one, the third thing, it's not a behavior, it's rather a precondition, because this precondition happened with multiple behaviors. I've quoted it as a separate behavior. Now in driving, there's one thing that annoys many people. There's one thing that people always need to be careful of. Suppose this is a very slow moving vehicle. It sees this trajectory, it says it's feasible, and it says that I want to travel by it. It travels by this trajectory, it reaches here without collision, without colliding with this vehicle, and that seems to be good. But the problem is that now the scenario would be, because this vehicle was very fast, it would be here moving very fast, while our slow vehicle is out here again moving very slow, and this distance is too less for this vehicle to stop in order to collide, in order to stop a collision. This is where it happens when we drive out here and we suddenly see that a slow moving vehicle has done a lane change and it's now ahead of us, and we need to brake rapidly. This is the same scenario. Or let's say this was a bicycle which turned a little towards the left, and it did not see a very fast moving car out here, and the car needs to steeply slow down. So we need to stop such things from happening. So I'll not be saying this again. I in fact did not say previously, or I'll not be saying this again. Whenever I'll be using any behavior which causes even a little bit of lateral change on the road, either clockwise or anti-clockwise, it causes any steering left or right, I'll be always seeing whether lane change behavior is true, or I'll always be seeing that I do not come ahead of a very fast moving vehicle. And by the way, if the fast moving vehicle was very far off, then this is allowed. So I'll be saying that if this purple trajectory can be if this trajectory can be tracked, and after tracking it gives enough time for this vehicle to slow down to avoid any collision, then this would be called as valid. So this is just a simple condition that I would be checking whenever any left or right turn is involved, and if it happens to be true, or if I'm not coming ahead of a very fast moving vehicle, then only that behavior would be called, else that behavior would not be called. That behavior cannot be exhibited, that behavior is dangerous. And as I said, this is the most important behavior. It'll go extend across many slides in this presentation. It's an overtaking behavior. So I have got a vehicle like this, it needs to overtake another vehicle like this. The first thing I'm of course trying to generalize this diagram out here. So the first thing that I would be generalizing is a definition called as the vehicle to be overtaken. So I'll try to find out how can this vehicle to be overtaken be identified. I'll be trying to find out of multiple options which one will be my D vehicle to be overtaken. It can be only one. The second thing I'll try to find out is whether overtake should happen in the left side or in the right side. So this will be my first problem, and my second problem will be deciding the side to overtake. The third problem would be that suppose in scenarios like this, my vehicle can nicely fit in over the right hand side and it can still overtake even if this vehicle does not move at any particular side. In other scenario like this, now these two vehicles need to move in order for overtaking to be feasible like this. If these two vehicles do not move, if this does not move towards the left and this does not move towards the right, overtaking will not be feasible. So that is my third will be my third problem, deciding whether the vehicles need to move, depending on which I'll call this as direct overtaking, where overtaking can be feasible without other vehicle moving, and this as assistive overtaking, when the other vehicles have to move, they have to cooperate. If they do not cooperate, overtaking would be infeasible. And after I do all this, I basically need to decide the point of overtake, and I simply need to construct a trajectory to that. That is what will initiate my overtake, not complete. That is what will initiate my overtake. So we come to the first problem, which was selecting the vehicle to be overtaking. Now we know that in this scenario, even if overtaking is possible by kissing this vehicle, it's a very dangerous thing. The driver will not do it because of the minimum separation that had to be guaranteed on driver aggression factor. So I kind of elongate this vehicle to a larger point, and any vehicle lying ahead in this region needs to be overtaken. Now here we see that there are three vehicles which are candidate and they need to be overtaken, but only one of them can be called as the vehicle to be overtaken as per my problem 1, which I'm dealing with right now. I lay down two criteria. Firstly, the vehicle needs to be the closest in terms of longitudinal separation, and secondly, it needs to be close in terms of lateral separation. I do not select this vehicle because it's too far ahead, and I do not select this vehicle because it's too laterally in the opposite direction. So this would be called as my vehicle to be overtaken. And of course, this vehicle needs to be faster than this vehicle in order for overtake to be initiated. Else, this vehicle is simply following this vehicle and no overtaking is necessary. Once I decide which vehicle is it that needs to be overtaken, my second problem would be to see if it's a direct overtaking or it's an assistive overtaking. Now here I see very nicely that this was the minimum separation that the vehicle required in order for overtake to happen, and this separation is available in left side, and in fact this separation is also available at the right side. So either of the side can host the overtake. I can easily overtake like this, or I can easily overtake like this. In general, even if separation is available at one side, I will call it as the case of direct overtaking, which was my other problem, and I will initiate the and I will go forward initiating the overtake. Now, the third problem was deciding the point of overtaking. Given that overtake is feasible like this, the separations are available immediately towards the right or the left, I need to decide the side of overtaking, and I need to, once I decided the side of overtaking, I need to decide the point of overtaking. So my side of overtaking is very simple. If I move towards the right, then I'll overtake from right, and if I move towards the left, I'll overtake from the left. So here it's obvious that this vehicle is moved towards the left, so overtaking will happen from this side. Had it been a scenario like this, overtaking would have happened towards the right, where this vehicle is towards the right. What we have is a scenario like this, where this vehicle is moved towards the left, and hence overtaking would happen towards the left like this. So my side has been decided. The other thing is deciding the point of overtake. I'll reset the graphics. Now I see this much separation is available for the vehicle to place itself. I know this is the separation that it needs. So based on again separation maximization principle and the principle that the maximum threshold has already been fixed, I can decide what is my point of overtake in terms of the lateral separation. So in other words, that I know in this I know that this is the separation that can be used for overtaking, and this is the separation that's actually needing. I can decide how my vehicle would place itself when it comes in between of the two vehicles. using the same principles of separation maximization. The point is that my distance in terms of the y dash axis has been decided. I need to decide the point in terms of my x dash axis, or I need to compute this distance. My point specification is my x comma y, so I've decided my y and I need to decide my x. Now we use a simple formula that takes as its input the total lateral deviation, or the change in y axis, or the change in y dash axis that the vehicle needs to perform. The larger this distance, the larger be this separation. So that's what I say. My delta x dash is directly proportional to my distance d, where my distance d is the total lateral deviation that the vehicle faces. And hence I can calculate this point. I've calculated the y point, I've calculated the x point. And once I know this point, I can simply construct this trajectory like this, that joins my initial point to the point of overtaking. And the second point is the second type of overtake is scenario like this. Now this was a separation needed, and this was a separation available on the left, this was separation available on the right. None of them are large enough. My vehicle cannot fit in like this, and it cannot fit in like this. Collisions will happen. So I see if assistive overtaking is possible, and now here I see there's a pack of vehicle which are moving almost parallel to each other. I see how much total separation is available. So this separation, this separation, this separation, this and this separation, I add it all up. I see, oh my god, such a large separation available. This is what is total available, assuming in the future these vehicles cooperate to make the overtake possible, or this vehicle moves a little here, this moves a little here, this moves a little here, and this moves a little here. So they all cooperate in order to make the overtaking possible. This is the total separation available. What I have done is that I have subtracted a small minimum safety distance, or the small minimum driver threshold, or the minimum driver aggression factor distance from each of these distance, and then that is how it's come up. Now this was what was needed, this is available. So I say the assistive overtaking is feasible. Then I need to decide the side, and then I need to decide the point. So my side is, again, this is more towards the left, so my overtaking will happen towards the left. And my overtaking point is critical now, because clearly the vehicle cannot place itself like this. Now I know, I've already assumed cooperation, I've already assumed that in the future these vehicles will move. So I know that this vehicle is trying to move here, this vehicle is trying to move out over here, this vehicle is trying to move out over here, and this vehicle trying to move out over here. I need to place myself such that as soon as I get the enough separation, and I know that my overtaking will be in between these two vehicles, these two have already been marked. So I know when I get the enough separation, in future when these two vehicles are out here, and these three vehicles are out here, and these two vehicles are out here, which is the best position that I can be, and that's exactly in between these two vehicles. So that is what where I would aim to be. This is in between these two positions laterally is what I would aim to be. So I've again decided my y dash axis value. I need to decide my x dash axis value. This is the separation. This is the d. I can use the same formula to calculate this distance. Now you see again d is very low this time, and hence this distance is much lower than the previous case. And I can use this trajectory for my navigation. Now one little catch here which I would be showing in the simulation results is that if a scenario like this happens where this separation was not large enough, and hence the vehicle had to go by assistive overtaking. Now there are two vehicles that are planning to go for assistive overtaking. They both do not see each other, and they both plan trajectories like this. Now it's obvious that the two vehicles cannot at any time simultaneously come in between. So only one vehicle is allowed to overtake, and what in simulation results we'll clearly see. I haven't shown all the behaviors, so we cannot discuss in detail now. That the more aggressive vehicle will ultimately succeed in overtaking. So if this is the more aggressive overtaking, this will overtake, while this would slow it and nicely wait for this vehicle to overtake, and then it will try to overtake. This is what will practically happen if both have equal aggression factors, or if both are equally aggressive, then they'll simply start following each other. That's what I would be taking in the simulation results. And once I know that I decide the side of overtaking, the point of overtaking, I'm taking this trajectory out here, then all these vehicles would be expected to move out in this direction. That's why a behavior we'll be seeing immediately after this one. Now, one thing to observe is that in the future I would be here while these vehicles would have moved a little ahead, and some of them would have created more distance. The overtake is still not it's still not happened. Now what will happen is that again, at when the vehicle reaches here, again assistive overtaking would be called, if it is still feasible. And now this vehicle would have moved by an even larger distance in between, and these vehicles would have been pushed even larger. Again assistive overtaking would happen. So this vehicle is continuously pushing these vehicles to turn at this sides until the necessary separation has been made available. This vehicle will continuously push, and either when the distance separation is available because of these vehicles nicely coming like this, or by some other factors, would overtake be possible, and this vehicle would overtake the vehicle pack. Correspondingly, at some time it may happen that assistive overtaking is proved to be infeasible. So out here, when I add up all this distances out here, they come up to be less than the distances that is required, which may be obviously due to some nice big vehicle lying out ahead. In which case the assistive overtaking feasible would be false, and even though initially attempted, the assistive overtaking would return false, and the vehicle would now show us any other behavior apart from overtaking. So that's what this cycle comes about. I'm continuously seeing, is overtake feasible? Yes. If overtaking feasible, continuously push the other vehicles left or right till the required separation is available. When the required separation is available, simply overtake. In fact, in some cases, direct overtaking would be possible at a later stage of time, in which the separation is available at either side of the vehicle, and the vehicle would go forward in overtaking the vehicle. And that is what I said, the corresponding behavior would be being overtaking behavior. And the behavior is very simple. Earlier I said I'm planning for this vehicle which needs to overtake this vehicle, so this vehicle will come out over here. And in assistive overtaking, I said that if there is already a vehicle here, this vehicle will need to dip a little towards the side. Now I'm basically planning for this vehicle. I'm seeing that there is a vehicle trying to overtaking, so I'll be constructing a behavior which makes this vehicle a dip a little towards this side, which is my be overtaking behavior here. Out here, so all the basics will just convert. The basics will remain the same, they'll just be opposite. Now I'll be seeing a faster vehicle behind, a slower vehicle ahead. So I'll be seeing this vehicle. I'll be deciding which side does it overtake, and I'll be deciding my corresponding side in which overtaking needs to be shown, and I'll be calculating my point of being overtaken. So the first problem, which is to decide the vehicle behind, is very simple. I'll be simply selecting the closest vehicle behind. Earlier I was selecting the closest vehicle ahead, laterally and longitudinally. Now I'll select the closest vehicle laterally along the axis behind. I'll be saying if this is more towards the right, it will travel overtake on the right, and hence I must be overtaken in the left. So using the same principle as before, I'll be selecting the side of overtaking, and once I have selected the side of overtaking, I'll basically be deciding how much I should move. Now I cannot travel so close near the road that my separation gets compromised with this vehicle enjoying too much of separation. So I'll be using the same principle of separation maximization, visualizing a point like this where this vehicle comes and overtakes this vehicle, and I'll be trying to maximize separation, keeping the separation maximization principle and the maximum and minimum driver threshold intact. And that is what you see out over here, that I have taken a vehicle behind. I have said that this will be the vehicle being overtaken. Of course, here there was no other option. So the else the closest could have been taken as a vehicle being overtaken. This will overtake towards the right, so I need to dip towards the left. In this region, there's a large separation possible. So my driver aggression factor gets predominated and I move out over here. Again, I first calculated how much do I need to dip towards the left, and using the same formula which converts this distance into this distance, I calculate this point over here and I construct this trajectory. If seen for this vehicle out here, by a similar analogy, this is more towards the left, so this will dip more towards the right, and this will be what will be my being overtaken trajectory. In fact, what I intentionally showed for this vehicle is that I'm calculating for this vehicle. So there are two candidates for vehicle to be overtaken. This is closer, so this one will be the vehicle to be overtaken, or this would be the vehicle overtaking this vehicle. It's more on the right, so it must be overtaking on the right hand side, so I'll need to dip towards the right. It's overtaking on the left hand side because it's more laterally on the left of the road, so I'll need to be overtaken by dipping towards the right. And how much do I dip towards the right? This is the separation available. This is the separation that it actually needs. Based on separation maximization principle, I'll calculate this distance, and based on this distance, I will calculate this distance. I'll select this point and I'll simply construct this trajectory. So again, the principles are same as the overtaking vehicle, and the additional clause is of course the assistive overtaken, where we had such a situation like this. Now, even if this vehicle knows that it's overtaking like this, so even if it turns by the maximum possible value, it does not get enough separation because this vehicle has to move. So in case even compromising the maximum distance does not enable overtaking to be happen, what this vehicle would do is that it will try to give the maximum separation that it can, and hence in the future it will be found like this, where this is the minimum driver threshold separation or the minimum driver aggression factor, and wait for things to happen in the future where this vehicle also does the same thing, and the overtaking is hence feasible like this. So in case you cannot give separation that is needed for overtake, just simply give the maximum separation that you can give, and that completes the difficult part of it, or that completes the most irritating part of it, which is the overtaking behavior. Now on, the behaviors would be very simple, and this is the first one of them. Now I see that this separation is very low and this separation is very high. So what I would like to do is to drive somewhere at the center. If this distance was less than the maximum driver threshold possible, else steer as much as that maximum driver threshold or the maximum driver aggression factor can be maintained, or the maximum that the driver intends to keep distance can be maintained. So based on that, I'll be selecting this point, and correspondingly to which this distance would be selected. And that's what we practically see. Suppose this vehicle is coming very close to each other, we steer out in this point. We plan to steer away from this vehicle and somewhere towards the center out here. So that's what's the minimum maintain separation steer behavior. and this would be called as the regularization point. Sometimes what would happen, again the same behavior as we saw in the previous slide is applicable. This is low and this is high, and so what it should do is that it should try to come across the center, but then here we see that even that does not help, because even if it comes at the center, the two distances are less than what my aggression factor states. My aggression factors did state that if the distance are too less, I'm not ready to take such a risk. And if I'm not ready to take such a risk, I should do something so that distance increases, and hence I simply slow down, which means that these vehicles will move ahead by whatever velocity they are going, and I'll drive slowly. So ahead, this would be the scenario where now I have a lot of separation available. I have the entire road in this scenario. Now, in a scenario where the vehicles are tightly packed like this, normally what would happen is that the least aggressive vehicle, suppose it was this one, the least aggressive vehicle would slow down, and in future these three vehicles would be here with nice separation ahead, and this vehicle which opted to slow down would be right here. So when we practically simulate, this is what would happen. And this is another behavior which is called as the discover conflicting interest behavior. So I consider a hypothetical scenario like this. This vehicle saw that this distance is very less. It said that I would turn towards the left, or let's say there was a vehicle to be overtaken here, to overtake which it was turning towards the left. In a completely parallel world, in a completely parallel sense, this vehicle out here saw another vehicle out here and it decided to turn right. Now this is what this vehicle is seeing and this is what this vehicle is seeing. They don't know that the other vehicle is turning left, and as a result they would end up in collision. So this is the discover conflicting interest behavior. Now one thing nicely that I did not speak about in the previous slide, but I had done, if this vehicle can be held for some time, the scenario would be that this vehicle initiates some kind of turn. Now while saying overtaking, not overtaking, or any other behavior, we always made sure that the vehicles are driving straight. If they are not driving straight, if they are driving tilted, the behavior was not called for. Of course, if they are driving in the opposite direction like this here, the behavior would be called for. So if we could have only controlled this vehicle for some time, this vehicle would have seen this vehicle traveling towards itself, and hence it would have not called the behavior. It would have done something else except for instead of trying to overtake. And conversely, if we had stopped the other vehicle for some time, it would have seen the other vehicle coming and it would not have initiated the overtaking. To again repeat very briefly, this overtake would only be possible if this vehicle is either driving straight or driving like this. This overtake would not be called if this vehicle is driving like this, because we know that we have computed based on this separation which is continuously reducing. So coming back to this scenario where these two vehicles are obviously overtaking because they did not know about each other, we constantly monitor the separation. If it falls below a threshold, we simply straighten the trajectories like this, the earliest that we can. And that's what the discover conflicting interest behavior does. It simply discovers conflicting interests, and if found, it straightens the trajectory. And my last behavior in the first set of single lane behaviors is travel straight, which simply which is simply called when no other behavior is possible. So there might be too many things happening out here, and it simply says I need to travel straight. I just need to take a unit move in the same direction, in the direction of the road, and that's always valid. Now, one thing we again have not been saying is that when I say travel straight, what I would basically do is that I will measure this distance and I'll decide what is my travel speed based on this. So I should have enough time to slow down or stop even if this vehicle suddenly stops down. So no collision would be possible if I travel straight, even though conceptually it may look that travel straight means traveling at a very high velocity or something. My velocity is completely different. I'm constantly seeing this distance and I'm adjusting my velocity so that so that no collision possible. And similarly, when I said obstacle avoidance using this trajectory, what I actually meant is that the distance ahead would always be monitored. So when I see a vehicle like this, I'll say that this is the distance that is available and I'll constantly adjust my speed so that first this vehicle goes and then this vehicle goes. So in this scenario, what again I would be showing in the experiment result, what will happen is that this vehicle will slowly and slowly travel like this until this vehicle completely overtakes, and when this vehicle is ahead, then this vehicle will start to avoid this obstacle like this. So in any case, I'm measuring this distance in front, I'm measuring the distance in my trajectory or from the vehicle in front, depending upon if whatever behavior is being called, and I'm converting this distance into a safe speed, and this would be the speed by which my vehicle would be actually traveling. And with this I come to the after overtaking, the next most important behavior, which is a very interesting behavior. I had a road like this. This vehicle overtook this vehicle in this manner. So in conception, this behavior is very simple. I'll basically be constructing this kind of trajectory. I'll be seeing whether this trajectory leads to a feasible single lane overtaking behavior, given that these vehicles keep on moving in the same speed, in the same direction ahead along the road. Positional and velocity uncertainty is added. So if this is feasible, I should simply track this trajectory and my overtaking behavior should be completed, which means it should be a single behavior and not a collection of three behaviors which I have shown like this. But in reality, what will happen, I'll construct this trajectory, I'll see that this is absolutely feasible, but later on what might happen, there might be a vehicle coming like this, and now the behavior does not sound to be very feasible. It sounds to be very risky because of this additional vehicle out here. So while I'm displaying this behavior, while I'm traveling with this, I'll always check for the feasibility, whether the behavior is still feasible or some uncertainties or some assumptions at the start have now led the behavior to be infeasible. If it's infeasible, I'll immediately cancel. If it's not feasible, I'll continue. So this was my behavior one where I initiated, but then I said that I always need to check whether the behavior is still feasible. If it is infeasible, I'll show a different behavior, a B2 here, when I will cancel the behavior, when I'll cancel. And of course, if it is feasible and the vehicle nicely overtakes this vehicle out to here, this was a vehicle to be overtaken, this was the overtaking trajectory, it overtakes this vehicle nicely, then it needs to return, which will be my very simple behavior or the complete behavior, which simply places the vehicle on the correct side. So that's what will be my single lane overtake. Next, I would be dealing with how to initiate, how to check for feasibility, and if infeasible, cancel, and how to complete the behavior. These are the three things that I would be dealing, along with when the vehicle is here, how does it travel, how does it, there might be obstacles out here, there might be some other vehicles out here, so how does it avoid these obstacles and other behavior. These are the 4 points that I'll be addressing in the next few slides. And the first one is, of course, the initiation of the behavior, which was my B1 in the previous slide. At any general scenario like this, I'll always check out these separations that my road should be wide enough for the two vehicles to accommodate simultaneously. So suppose there was any other vehicle out here that was going in this direction in the right side, my three vehicles cannot accommodate simultaneously on the road now, and hence it would be called as infeasible. Correspondingly, I cannot initiate a single lane overtake behavior here if there is an obstacle like this. Enough separation is not available. So in this entire region, I should have enough separation for this red vehicle to be accommodated, which is my most important precondition. My second condition for this behavior to happen is that given that condition 1 is true, or the vehicles have enough lateral separation for this vehicle to be accommodated, my second condition, I then make in this trajectory which is called as single lane overtaking initiation trajectory. And how this trajectory is made is based on again the principle of separation maximization as well as the maximum driver aggression behavior threshold. I calculate this point laterally. Once I've calculated this point laterally, I can calculate this point longitudinally, and hence I calculate this point and I construct this trajectory. I haven't considered this vehicle. I have only considered this vehicle, which was the vehicle to be overtaken by the same definition as in normal overtake. So by the same definition, I calculate this point out here and I make this trajectory. Of course, right now the behavior is very simple to the direct overtaking. Similarly, I selected the vehicle to be overtaken, and by similar methodology, I selected the point. The single lane overtake can only happen at the right side, also it's not a single lane overtake, of course. So I calculated this point. I made in this trajectory only considering this vehicle right here. I said how would the subsequent movement take place. Well, I say this vehicle is traveling at the speed, say v1, and this vehicle is traveling with speed v2. I say approximately by how much time and by how much, after how much distance would I have overtaken this vehicle out here. I say after how much time would I have overtaken this vehicle out here, and after this much amount of time, I can simply calculate this distance based on the concept of relative velocities. So when this vehicle is sufficiently ahead of this vehicle out here in future time, I'll calculate a trajectory very similar to this trajectory, except for this will take me back to the correct lane after the overtake has been completed. So this is the trajectory that I have calculated. If I can simulate this vehicle, and all the other vehicles, including positional and velocity uncertainties, and tracing this trajectory causes no collision, then I'll say single lane overtaking is feasible. Now remember, I have constructed this trajectory considering only this vehicle and no other vehicle, so it's kind of prototype trajectory. And I say that is this prototype trajectory valid? If valid, overtaking is feasible. So that was my B1, which was the important part of this behavior. While I am over here, while this vehicle is out here, which means that it has successfully entered into the wrong side, or it's still entering into the wrong side of this dual carriageway. How does it travel in general? There might be some obstacle out here, there might be a vehicle, it will have to surpass this obstacle like this. It might have to again use the principle of separation maximization to decide what separation to maintain from this vehicle. So there might be a lot of things happening here. So I say the rules that have been displayed so far are all valid here, except for overtakes are not possible. And when I say overtakes are not possible, basically what I mean is that I was out over here, I see a vehicle out here, I cannot overtake this vehicle like this. Obviously, it's very dangerous. We never do that. So except for overtaking, all the other behaviors are possible, which means the vehicle will continuously adjust its lateral position depending upon the other obstacle and the vehicles out over here. Again, it's still an unorganized or chaotic travel. And this would give me the trajectory of or the path or the steering required. The other concept is the speed. The other concept is at any time step, knowing the speed of travel, and in this entire process where this vehicle overtakes this vehicle out here while this vehicle was traveling like this, there are three types of vehicle. This is type 1, this is type 2, and this is type 3. There are only three types of vehicle. If there's any other vehicle moving like this will basically be a general vehicle out over here, or the vehicle of type 2. If there's a vehicle here, this will become the type 3 vehicle and this will become the type 2 vehicle. So my type 1 vehicle is the vehicle which specifically is performing a single lane overtake, and my type 3 is the specific vehicle which is the first heading vehicle out here, and all other vehicles are type 2 vehicles. So I need to fix speed mechanisms of these three types of vehicle. Now this is the general vehicle. So their speeds are fixed exactly as we saw. So suppose there was an obstacle or any other vehicle here, this distance would be measured d and it will be converted to speed. A safe speed as we saw in the previous slide. Type 2 vehicles only see the distance ahead, and based on that the distance they compute the safety speed. Type 1 vehicles do exactly the same. Now when I was dealing with type 2 vehicle, I basically said there might be an obstacle or there might be any other vehicle out here. So the worst case scenario would be this vehicle will immediately stop for no reason. It might immediately stop and I need to take that into account. So my distance d is known. My speed has to be large enough so that I can slow down, maintaining sufficient separations after I slow down. Even if this vehicle it suddenly slows down, it brakes instantaneously, it brakes rapidly. This was my general phenomena to fix the speed of type 2 vehicles. With type 1 vehicles, I cannot use the same worst case analysis, because the worst case analysis would be there's a type 1 vehicle and there's a type 3 vehicle. The worst case would be that this vehicle it accelerates infinitely, in which case collision will happen. So I don't use the worst case analysis as I had used in type 2 vehicles. For fixing the speed of type 1 vehicle, I simply say that let this vehicle be following at a constant speed. I should have enough time to slow down to avoid any collision. So again, the same distance d is related to speed v, except for in this case the vehicle is traveling in the opposite direction. The relative speeds are different and I consider this vehicle to be moving. The basic funda of both these type 1 and type 2 vehicles are the same. And for the type 3 vehicles, there is a different phenomena that happens. In the worst case, what will happen is that my type 1 vehicle is moving here, and in the worst case, my type 3 vehicle is moving here. If I use the same phenomena that I had used in fixing the type 1 vehicle into type 3 vehicle, which seems like a fair strategy, I say let this vehicle assume this vehicle traveling at a constant speed v, keep enough distance so that you can stop and not collide. What will happen in the future, my scenario would be like this. Now again, no collision happened, fair enough. The vehicles did not collide. They have some distance available, but the problem is my red vehicle or this vehicle is traveling in the wrong side. It needs to return. and it has got no space for that. It cannot turn in that sharply. So I cannot use the same phenomena as I had done for type 1 vehicles. I'll have to find out something else. I'll have to do something better. So what do I do is that this vehicle knows that this vehicle will ultimately have to return in its original lane. Suppose a red vehicle was here. This vehicle asks if it returns immediately. How can it return? It can return using some trajectory like this. And it sees this distance out here, which is the separation available. This vehicle, it plans so that it can stop well ahead, so that the red vehicle here, it has enough time, or it has enough separation to return to its original lane. So again, this was the thing that was haunting me. This was the thing that was scaring me, that I said these two vehicles facing each other, moving much, facing each other and stopping, so that this vehicle does not have enough separation available. I have only made a very small change, and what change is that? I have say this distance is d1, that this vehicle needs to correct to go to its original lane. I now say that my blue vehicle out here, it needs to stop before this line. It compulsory needs to stop before this line. If it exceeds this line, this vehicle will not have enough distance to go back. And all these things, of course, we will be seeing as a simulation scenario very soon. These are only the general principles. So that's how the speed is fixed. Important point back here is that I do not fix in the speed of the red vehicle. So this was a red vehicle, this was a blue vehicle out here. I do not say that this is the distance that the red vehicle will take to return, and therefore I should stop out over here, because if I stop out over here, I have basically stopped. I need some speed to return back. That's why we are not using this nice, excellent speed change mechanism that we have done for this vehicle. We are not using for this vehicle, because this vehicle cannot stop out over here. This vehicle will have to stop, return to its original lane, while this vehicle has to stop out here in order to make this vehicle go back to the original lane. And the last couple of behaviors, which I'll briefly take in. Now, I need to decide at any time whether my trajectory is still feasible, whether my single lane overtake is still feasible, and the only thing that can cause infeasibility is this vehicle out here, which is approaching in this direction. So I say immediately, if I need to return back, what is the best trajectory, what is the worst trajectory that I can use to immediately return back, and that is this trajectory. How this has been calculated, I have used the distance of I have used the separation maximization principles to calculate this point, corresponding to which I have calculated this point, and I've connected them by trajectory. So that is the earliest trajectory that will take me to the correct side. This much part of this trajectory is in the wrong side, and this much part of this trajectory, basically this much part is in the wrong side and this much part is in the right side. So this is the threshold distance before which this vehicle will have to stop, what I presented in the previous slide. If this separation is not available, so let us say if my green vehicle is actually out here and this separation is not available for the red vehicle, it means that the alarms are high. The minimum distance that I require to go back, computed after some safety distance measures, the minimum distance, I do not have even that. So I need to immediately move back. In other words, I'll again draw, if my green vehicle was like this and this trajectory was little infeasible, this red vehicle will be told cancel the single lane overtake, go immediately back, and it will normally mean that it traverses this trajectory, and of course we know traversing this trajectory will mean collision with this vehicle, so it actually does not traverse this trajectory. It extrapolates the movement of this vehicle, it computes this distance, and this distance is converted into the current safety speed v. What practically it'll when we simulate, what of course I'll be showing in the simulation results, what we would be seeing as this vehicle would be going up here, it will be almost waiting at this point till this vehicle crosses, and after which these two vehicles will follow each other while this vehicle is going in this direction. So that would be shown in the simulation. The point is, if the minimum distance that is required to go on the correct side, even if that is not available, immediately cancel everything and go to the correct side. And the last behavior is, of course, when I am way ahead of the vehicle which was the vehicle to be overtaken, enough distances separation is available, and I can nicely construct this trajectory assuming the hypothesis of separation maximization and driver aggression. I can easily construct this trajectory even though a vehicle may be coming here, and I can nicely trace this trajectory. I'll say that my overtaking is complete, this vehicle is ahead of this vehicle, and I have separations available. I'll simply return back, and I said it is a rule based approach, so everything will have a precondition, it will have an in behavior specification which I'll want it to do, and it will have a priority. This is what summarizes, this is what has been placed in almost a rule form. This is if precondition, and this is the then action part of it, and this is while traveling, while showing that behavior, what it does, and the priority. So as you would appreciate that the descriptions are not in a very mathematical form, they are in a very vague format, because I'm using deliberative means to calculate each one of these preconditions, how I've just shown you. And similarly, the actions are not very formalized, it's not mathematically formalized, because I'll be using deliberation to calculate the actual actions, and similarly how my vehicle moves. And with this, I'll come up to the results. This is the vehicle always stays at the center. If there's a sharp turn required, this takes the best possible of it in all these scenarios. This is the obstacle avoidance point. It almost avoided it at the center. Again, it avoided it at the center. Here is where it was here when it saw this obstacle and it took the central route. Here is, as I said, this vehicle here sees this vehicle. Now it needs to avoid this obstacle using this trajectory out here, using this nice little trajectory, but it will have to wait for the green vehicle. First the green vehicle goes, and then the red vehicle goes. These are the overtaking behavior. It simply overtakes. Here the green was more aggressive, the red was less aggressive, so it took an aggressive overtake. Here the red vehicle became conscious and it dipped a little, and this is the assistive overtake, where here is where overtaking happened, and this red vehicle had to dip, it had to cooperate in order to make the overtaking possible. And I'll play in a very complex formulation which has multiple of those things happening. Now here what you see is that two vehicles had to overtake. I'll just pause in for a second. Here first the pink vehicle overtake this vehicle, and this was a more aggressive vehicle, so it was constantly pushing both this vehicle in front, and the red vehicle was pushing the green vehicle using the overtaking norms. As I said, this was being pushed because of the overtaking behavior, this was being pushed because of the maintain maximum separation behavior, and because this was more aggressive, it got the chance to overtake. And now the blue vehicle will overtake. It will push both these vehicles behind, and this is where what I said, that when we keep the overtaking, when we keep the aggression factors equal, this is pushing the red vehicle by an amount equal to what the blue vehicle is pushing the green vehicle, so nothing happens, and the green and the blue vehicle push each other in turn by an equal amount. So all the pushes get cancelled and nothing interesting happens. And they simply follow. And these are the single lane overtakes behavior. Where it is feasible, it happens. Where it is infeasible, doesn't happen, and later becomes feasible and happens. And this is when it is feasible, but later on it was found that it's infeasible, and the blue vehicle simply returned. Until later it became feasible. And that is what I said. If we take a hypothetical road like this, the most aggressive behavior vehicle will travel right ahead, followed by the middle aggressive behavior, followed by the least aggressive behavior. And that would be for the presentation. Thank you.